Hi, my name is William Armstrong. Very honored to be here at EXAG. And he already said the title, BizMC. So I was originally inspired to pursue computer science for my interest in speed running, which you all probably know about, the competitive act of playing through a video game with the goal of completing it as quickly as possible. I think most people are aware due to charity events like Games Done Quick. Popular speedrun records are the result of thousands of attempts by runners and years of refinement. And motivated runners become motivated to reverse engineer the game to perform extended testing on them to see what the optimal route through the game is. The YouTuber Summoning Salt does detailed videos on the evolution of speedrun records. They include some of these discoveries. And there's also a book called Speedrun Science that kind of goes into detail the process of kind of glitch hunting and analyzing games. So tool-assisted speedrunning is the act of using an emulator to produce a theoretical perfect speedrun using tools built into the emulator, such as frame-by-frame input manipulation, the ability to create and load save states, backtrack, essentially play through the game with perfect accuracy and precision. These may show off glitches and manipulations that are not humanly feasible, but discoveries made in the production of tasks are often incorporated into speedruns to help refine them further. So pictured there is an example of a built-in task editor that shows which inputs are performed on each frame, and it can be backtracked and manipulated. So BizHawk is a popular emulator for tasking, features support for dozens of consoles. Also built into it is a Lua console, which allows for the creation of utilities to assist in task production. So this is an example that comes with BizHawk for Mega Man 4, which is a hitbox script. What it's doing is it's loading memory addresses, identifying all the objects on screen, and basically displaying their hitboxes and hurtboxes while the game runs, just to help anticipate collisions. So Lua scripting in BizHawk involves access to the game memory, controller input, and save states. Scripts can be written to play through a section of the game automatically, as well as reload the previous state in order to test multiple branches. Thus, it's ideal for automating sections of a task that require repetitive brute force testing with simplistic input. For example, in a role-playing game like the Pokemon games, it might be necessary to manipulate or re-roll a character in order to obtain optimal statistics. And there are two approaches to AI playing video games. One of them is what you call general video game playing, which are algorithms that develop a winning strategy with minimal human interference. They kind of figure out the best strategy really in the absence of knowing anything other than the most basic rules. And then another one is to manually port and simulate the game logic. I think one of the best examples of this on the task video site is this Arkanoid task, which is done by reverse engineering or rewriting all of the relevant gameplay logic in C++ in order to eliminate all of the emulator overhead and any unnecessary code having to do with, say, video or audio processing. But even in doing that, the author said it took him a whole year of processing time on 6 cores to brute force the entire game. So my intent was to have something in between these two, which is a way to leverage useful information the author already knows about the game without needing to fully reverse engineer it. So we've talked about this, and I think everyone's pretty familiar with it. Monte Carlo Tree Search. Search algorithm determines the best move by iteratively building this tree of game states. Each iteration consists of selecting nodes, expanding nodes, simulating the remainder of the game or rollout, and updating the tree or backpropagation. MCTS is shown to be an effective algorithm for strategy and board games. So my intent is to create a framework for task creators to develop game-specific modules which define the search space and allow for the underlying MCTS algorithm to run in BizHawk rather than needing to reverse engineer and port the game logic to some kind of external tool. So to develop a module for BizMC, the author will need to define the following. First, given a game state that is currently looking at what actions are available, This example is just a game of Othello. Very simple, and obviously you can look at that and see which moves are available to the current player. You can either do that just literally by looking at and analyzing the graphics on screen, or you can actually look up the relevant memory addresses. Then we need to explicitly, we need to have a way of actually executing the moves that we've identified. So in order to do that, in BizMC, we assign each distinct move a unique string identifier. And then from that, we're able to define which controller inputs or manipulations need to be done in order to execute that. For example, if we define moving to that spot as 1-3, then we can either say in the execute function that the way you do that is you move left and then up until the memory address of the cursor matches the target. Or alternately, what you can actually do in Lua, BizHawk Lua, is manually write that value to the X and Y memory addresses of the cursor, and it may actually automatically move there. That's a sort of shortcut you can take as long as it doesn't alter the game function any other way. You can kind of do a little bit of cheat like that to save some time and effort. And then third, what's the rollout behavior for forward simulation? By default, it will just be random moves in BizMC, but obviously you can define something a little more sophisticated, like simply just a greedy thing where you choose the move that gets you the most tiles. And then what's the objective? And since this is designed for speed running, a lot of times the objective is to lower the frame count, which is just literally just looking at the emulator's current frame count, minimizing it. In this case, it could be either maximize your chances of winning or try to get the most tiles at the end. And then end conditions, you need to have a way to know that it's over. And that can be looking at a memory address associated with the end of the game, either winning or losing. Or you can actually, in the process of reverse engineering, actually identify like a specific line of code in a function that only runs when the game has ended. And you can actually link that in the code, and it will be like a trigger, registered trigger function. So, like I said, in order to write all this logic into our module, it is necessary to do some degree of reverse engineering. And here are kind of three of the main tools I used that are built into various emulators and other external tools. So memory search is the most useful. Allows for relevant memory addresses to be identified by systematic testing. For example, the in-game cursor can be very quickly located in memory by moving it around and seeing which addresses increase or decrease. Then there's a debugger built into a lot of emulators, and that functions just like a debugger in most like IDEs, which is one of the memory addresses that you've identified, you can set breakpoints for it, and you can locate the functions in which it gets modified. And then the third one, which actually helps a lot, is if you use something like Ghidra, there are loaders written for platforms like the Game Boy Advance. They'll load a game in, it'll do like a preliminary processing and isolate all the functions it can find. And then from there, you just sort of fill in the details, like what you think the return type is, name the function, name the variables. And through that, it'll decompile it for you and give you a pretty good understanding of what it's doing. That was a really useful tool, especially for Game Boy Advance games. So what I was talking about before, when you register sort of register a function to set the end flag in order to know not to try to pursue it any further, you need to link it to specific memory addresses. And so, for example, Super Mario Brothers, any of the following could be a trigger that the current level is over, either you won or you lost. So a line of code that runs only on the death sequence, like the death or victory sound effects playing, is light counter decreasing, the screen fading to black, like a specific sprite, like the one that came grabbing the flagpole at the end. Those are all things you can say are end states. you could register them to a function and it'll automatically stop and sort of say that that node is terminal. Then also there are times where you can sort of use that to also prohibit behavior that you don't want to happen, that you know won't be in the optimal solution. For example, when I ran this code in Super Mario Brothers, I wanted it to just run through the first level as quickly as possible. But I kind of reasoned that if it was going through the first level very quickly, it would never collide with the side of any objects. It would just jump over all of them. And so I looked in the annotated source code for this game, and I figured out the line of code that is associated with colliding with an object in the side. And I set that, and sure enough, it very quickly found a solution that avoided doing that. So that's one way to save time. Using registered functions like this is also a way to make your coding easier, because you can do things like, if in a strategy game you need to sort of wait through the enemy to get through all their turns and then go back to your turn, you can figure out which line of code is associated, for example, with like the menu popping up and your turn starting. You can just say, wait for this to happen. So this is kind of example, very simple example of some of the code where all it's telling it to do is just scroll through the menu to the person option and sort of see the explicit memory addresses it needs to read. It just sort of needs to hold either left or right on the pad until it gets there. And then after that, it'll proceed. So this is the first game I wrote modules for. I actually wrote 2 different modules. And this goal here is recruiting generals. So there's a command that allows you to attempt to recruit an enemy general to your side. Each month, each general in the province can attempt to recruit an enemy general through one of 4 methods called special, horse, gold, or letter. Each of these methods uses a different formula to calculate your % chance of success. If that % chance is greater than the current value in the random number generator, the action will succeed. Unlike a lot of other games, the RNG values in this game do not change on a frame-by-frame basis. They only advance when they're pulled. This means that the same sequence of actions in the same order will always have the same outcome, which means that the route we plan in this path will actually be able to be replicated on a real console, which I've done. So these are actually the 4 formulas for each of the recruitment types that I worked out. So when we're populating the list of possible actions the player might take in a certain node, we can use these formulas to automatically reject any actions that we know have a 0% chance of succeeding. And it's because sometimes we end up in a situation where the RNG value is very low and it's basically a 0% chance of anything happening. We also introduce an additional action called scramble, automatically advances the random number generator to the next value. This is functionally equivalent to choosing an option that generates a random value and then canceling out of it before you've made any actual change to the game state. Basically, is a way of manipulating the RNG without investing anything other than just a little bit of time. There's another mechanic to take into account, which is that as your general goes to the target province, it actually plays an animation, and for every province it visits, there's a chance he gets captured or intercepted, which causes the action to fail, regardless of whether or not it predicted it would succeed. So we have to set a endpoint breakpoint function for that happening. And then finally, the way it scores it at the end is that there's sort of 3 vital steps for each general, which is intelligence, charm, and war. And sort of it assesses how well it did by the sum of those values. So this is the second one, which is the battle sequences. And there's sort of 2 ways to win these. Either you defeat all of the enemy generals, or even more rare is that you actually walk onto the enemy sort of fortress or garrison. And if you can successfully do that, actually automatically wins the battle for you. The human and CPU armies take turns, moving 1 unit at a time. So the main ones, there's actually more, but more moves you can take. Just to simplify, I said move, attack, and this other thing called fire trick. And those can be done in each of 6 hexagonal directions. Using fire trick has a certain % chance of setting a fire, which in subsequent turns randomly spreads across the map, influenced by wind direction. So here's an example of it being all over the map again. Since the intent of this module is to manipulate fast battles for a speedrun, I wanted to find a way to just sort of cheat out a victory without having to build up or train my army. So like I said, capturing the enemy fortress is theoretically the fastest way to do it, but the game basically makes it impossible for you to do it by normal means because they'll put the strongest general there and just stick them there, and so just fortify it. But in testing it, I discovered there's a behavior, which is if this fire ever spreads onto an enemy unit, it will automatically retreat until it goes away. And you can do that to get fire onto the enemy fortress, they'll retreat, and you have a moment of time where the fire dissipates for you to hop back on and capture it before they return. So due to the complex nature of the fire, I couldn't figure out the game logic, it's pretty complicated. And also there's a very heavy degree of randomness to this set of circumstances. I think this is basically impossible. Very hard to manipulate normally. But because BizMC has the ability to sort of manipulate random events and test a lot of different branches, it was able to solve multiple battles this way. And like the previous module where it had a way of manipulating random values, occasionally in the solutions of this, you would see one of your units try to start a fire but fail. And it would do that intentionally because even though that didn't seem to do anything, it actually manipulates the RNG state. There's another interesting feature that I discovered in this, which is the game sort of has a branch instruction that differentiates between whether it gives you the player control over units or whether it gives the computer control over units. There's differentiating between player and CPU turns. And what I found is that I wrote a custom rollout function that actually bypasses the normal functionality and basically tells the game to make the CPU control your units. And it turns out that's a way faster way to get through your turns during the rollout function. It wasn't end up not being that useful because the behavior of the CPU is so different than this strategy I came up with. But I think it's a very promising thing to do for kind of speeding up writing the modules for turn-based strategy games. Am I cutting? Yeah, okay. Sorry. I'm sorry. Okay, so these are more strategy games. This is kind of the same thing. These are kind of the action types. There's a counterattack that kills. This is like a 3D maze game for the original Atari. All right, and then I'll just quickly go over this. So there's it was mostly designed for strategy games, but there's some other things like kind of action games, reducing lag, games that have a lot of lag. And then for like racing games, driving games, you sort of simplify the problem statement. It can be used for these too. So sorry, I kind of lost track of time. But I would just say in general, I consider it success. The need to reverse engineer game data does create like a hurdle, but I think this is promising. And I guess that's it.